All right, today we're going to learn about Newton's third law. Newton's third law. So, Newton's third law, you probably actually heard about it before. For every action, there is an equal and opposite reaction. And according to Newton's third law, forces always come in pairs. That is, there is no isolated force in the universe, not one single isolated force in the universe. The four forces in a pair are equal in magnitude and opposite in direction. This is the most important thing. People in my AP classes get this mixed up. The forces in a pair, the Newton third law pairs, they have to act on different objects. And we commonly mistake that fact, okay? So third law is very commonly stated: for every action, there is an equal and opposite reaction. And this is how your book presents this third law. Again, for every action force acting on an object, there is a reaction force acting on a different object. Notice the different object. The action and reaction forces are equal in magnitude, but they are opposite in direction. So let's look at some examples. This is a picture of a person who is pushing on the refrigerator, and this is their force. This guy is putting a force on that fridge to the right. Well, at the exact same time he's pushing on the fridge is pushing on him. So the fridge pushes on the person. So if I were to draw a dot to represent the person, this is the force we'll call this object 1 and this object 2. This is the force of object 2 acting on object 1. If I were to draw a dot to represent the fridge, this is the force of object 2 acting on object 1. Notice they are opposite in direction and they will have an equal magnitude. And they are on two different objects. Those are Newton third law pairs. Here's another example. This is the Earth. The Earth has a force of gravity that acts on the space shuttle. And whether you believe it or not, guess what? There is a force that the space shuttle puts on the Earth. They are equal in magnitude, opposite in direction. So if I were to draw a dot to represent the space shuttle, there is the force of gravity acting on the space shuttle, and that's from Earth. If I make a dot to represent the Earth, the center of mass of the Earth, there is a force that's equal in magnitude that's pointing upwards towards the space shuttle. And you could say Earth on the shuttle and the shuttle on the Earth. Okay, and they are, sure enough, equal in magnitude, opposite in direction. I'm not sure exactly what this object is in the third picture, but it almost looks like it's on an air track. But at any rate, there's the force that the person's putting on the object. There's the force that the object's putting back on the person. And I can draw a dot to represent the person's hand, if it will behave. And there is the force on the hand, and here is the force on the object. Okay, so these are some fun pictures. So a bug hits your windshield while you're driving on the highway. Which object feels the larger force? The bug, the car, or they both feel the same force? And the answer would be C, which is kind of hard to believe, but the force that each one of those feels is the same. Just because the car is bigger doesn't mean anything. The bug feels the same amount of force that the car feels. Mike Tyson punches you in the face. Which object feels the larger force? Your face. his fist, or they both feel the same force? And the answer is C. Okay. A large truck crashes head on with a small car. Which experiences the larger force? The car, the truck, or they experience the same? They do. Now, the reason why this car gets crushed has nothing to do with the forces, it has to do with the mass. Force equals mass times acceleration. The forces are the same. Now, the car has a very small mass there compared to the truck. Therefore, its acceleration is substantially larger, and that's why it comes to a brutal stop and gets crushed. All right, now we'll work a quick problem. Two groups of canoeists meet in the middle of a lake. After a brief visit, a person in canoe 1 pushes on canoe 2 with a force of 46 newtons to separate the canoes. The mass of canoe 1 and its occupants is 150 kilograms. The mass of canoe 2 and its occupants are 250 kilograms. What is the acceleration of each canoe? So I'm going to draw a dot to represent canoe number 1. And I notice that I have a force pushing to the left. This is force 1. And I have a dot that represents canoe number 2. This is force from canoe 1 acting on canoe 2. This is force from canoe 2 acting on canoe 1. Well, they told me this force was 46 newtons. Well, this force has to equal 46 newtons. And they tell me that mass of canoe 2 is equal to 250 kilograms. And they tell me mass of canoe 1 is equal to 150 kilograms. What are they asking for? They want to know the acceleration of this one, and they want to know the acceleration of that one. Well, force equals mass times acceleration. The force on canoe 1 is a negative 46 newtons because it's to the left, which equals 150 kilograms times acceleration. So acceleration is equal to minus 46 newtons over 150 kilograms, which is equal to I had to get my calculator, negative 0.31 meters per second squared. Does that make sense that canoe 1 would have a negative acceleration? Sure enough, canoe 1's going to move to the left. How about force? How about the acceleration of canoe 2? Well, force equals mass times acceleration. The force is again 46 newtons, but it's to the right, so it's positive. The mass was 250 kilograms, and we're looking for acceleration. So acceleration is 46 newtons divided by 250 kilograms. Meters per second squared. Now let's look at those numbers and see if they make sense. Well, this one's positive, which makes sense because canoe 2 is going to go to the right. This one's negative because canoe 1's going to go to the left. But look at the values. So the canoe number 2 is going to move to the right with a smaller acceleration than canoe number 1. Does that make sense to you? And why? Why does that happen? Well, look at the masses. So the forces are the same. The forces between the two are the same. However, the mass of number 2 is greater than number 1. And because of that, acceleration is less. Acceleration of 2 is less than acceleration of 1. So the forces between the two of them are the same, but the acceleration will be different based on their masses. That's what I have for you today.